Hi class, this is the second video on atomic structure and electron configurations. We just finished reviewing electron configurations and orbital diagrams, and what you see here in table 6.3 is just a list of elements with the number of electrons and the electron configuration and orbital diagram. It's a good idea to maybe just kind of cover this up and try these out and just check and make sure that you're fresh on these, and if not, let me know and I will try to get you to help you review so that you can make sure you know how to do this. So there's just a list of a bunch of electron configurations right there. Alright, I want you to look at this electron configuration here. We talked about some electron configuration rules on the past couple pages. We have the Aufbau principle, we have Hund's rule, and we have the Pauli exclusion principle, and we talked about those. Let's see if we can identify which rule is being violated by each of these cases. First question, which electron configuration rule is violated in the electron configuration A? Well, I hope you can see that we have an empty energy level down here at the bottom. So we tried to start doing this electron configuration, or this orbital diagram, on like the second floor of the building is the way I would look at this. So that is not following the building rule, which is the Aufbau principle. And the reason is because there is an empty orbital in the first energy level. Or you could maybe more easily say the 1s orbital is empty. Same thing. Alright, and then down here, which electron configuration rule is being violated by B? So what's not being followed by B? Well, I hope you can recognize the problem with this. If not, pause the video, take a look at it for a minute and see if you can figure it out. This is our problem. Those two electrons are facing the same way. We can't have two electrons in the exact same orbital that are facing the same way. That violates the Pauli exclusion principle. And it violates the Pauli exclusion principle because there are two electrons with the same spin in the same orbital. I also hope you noticed there's another rule that was being violated. So if you wrote something else, you probably just caught the other rule. There's another rule that's violated here, and it's Hund's rule. Because there's empty seats on this bus, and we doubled up before the whole bus was full. Or an actual way of explaining that would be because there are two electrons in the same orbital before all orbitals of the same energy are occupied. Probably another way to say that, but that's the way I would think about it, and I believe that is a good explanation. We have some empty orbitals of the same energy level, and we started doubling up before we filled, before those energy levels, or before those orbitals at the same energy level were occupied. Same energy level and sublevel, I should say. Which of these electron configurations would be an acceptable excited state electron instead of a ground state electron configuration? Well, this rule basically just never happens. But in an excited state, what happens is we have electrons moving from a lower energy state to a higher energy state. So not all of the electrons are in the lowest energy state. So the one on the left, A, even though it's violating the Aufbau principle, it can actually happen sometimes if it's an excited electron configuration, excited state electron configuration. A would be acceptable because an electron could move from a low energy level to a high energy level, or higher energy level. If it was excited. All right, that's the gist of that one. Good thought questions that you want to be able to answer. All right, down here we review the D sublevel. This is a little different. Don't forget, when you get to the D sublevel, you need to remember N, where N is your energy level, the row that you're looking at on the periodic table, N minus 1. So in the fourth row, or the fourth energy level, the D block is actually called 3D. In the fifth energy level, the D block is called 4D. By the way, we will give some explanation for why that is in this class. We can't really explain it in pre-AP chemistry, and it's still a little soon, but we'll get to it soon when we talk about PES, or photoelectron spectroscopy. Examples. We're going to complete the ground state electron configurations for the following elements. Instead of having you write out the whole thing, 1s2, 2s2, 2p6, we've given you the first little bit of it. So let's look at the periodic table. We're looking for Fe. It's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then I get to iron. So it's going to be 4s2. Don't forget the D block. We're going to go down in energy level. So it's going to be not 4D, but 3D, 1, 2, 3, 4, 5, 6. 3D6. So it's going to be 4s2, 3D6. All right, the next one's zirconium. 1s2, 2s2, 2p6, 3s2, 3p6. Zirconium is down a layer, so we're going to have to go 4s2, 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, there's 10 in that D block. And then 4p, 1, 2, 3, 4, 5, 6. There's 6 in the P block. And we go back over 5s2. And then don't forget, we go down an energy level, 4d, 1, 2. So 4D2 is where we're going to end. Let's write that out. 1s2, 2s2, 2p6, 3s2, 3p6, and then we said 4s2, 3d10, 4p6, goes back to that fourth energy level when we get in the p block. I don't know if I said that right when I was looking at it, but that's what you do. Go to the other side, and we would go 5s2, and then 4d, I'm going to have to look back because I've forgotten. Yeah, 4d2. That's zirconium. Bromine, Br. All right, bromine is way down here, so it's in our fourth energy level. It's going to be 4p5. It's in the fourth energy level, ending in 4p5. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d. Again, d is always 10. And then we'll have 4, 5. Go look at that again. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 4p, 1, 2, 3, 4, 5. All right, what about the F sublevel? Remember, it's n-2, so it's just like the D sublevel, except we go down 2. There's one more thing that kind of throws students off sometimes about the F sublevel. Let me just go back up a couple pages real quick. Remember that F sublevel, it fits right up here. It fits right up here. So it's actually the 6th and 7th energy level, but we're going to go down 2, so we're going to call it 4F and 5F. Back to the page we were looking at. We want to do the electron configuration for osmium. So they gave us the first part, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, and then 5p6. Then we want to pick up where we left off. So we went through to 5p6, which is 1, 2, 3, 4, 5. And then we have 5p6 is xenon, and then we go down to where cesium is. Got cesium and the barium, that would be 6s2. After 6s, we got to go down to the F sublevel. 4F, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. This throws people off a little bit because of just the way that the periodic table is laid out. Just know that it's always 4F, 14. And then we go 5D, 1, 2, 3, 4, 5, 6. So 5D6 is where we're going to end. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14. Then we have 5d. Again, osmium is 1, 2, 3, 4, 5, 6. 5d6. Then we get francium, Fr. We're going to go down to the same level, 6th energy levels where we're going to start. And I'm looking for francium, which is right here. Oh, this one's actually pretty easy if we're doing noble gas configuration, but we want to go ahead and do the full configuration. So 6s2, 4f14, 5d10, then it'd be 6p6, then 7s1. We're ending with 7s1. So after 5p6 comes 6s2, 4f14, 5d10, 6p6, and then 7s. Francium was 1. 7s1. All right, those are the hardest kinds of electron configurations to do. So if you follow that, you're going to be fine with electron configurations on the AP exam, I believe. Noble gas configurations, don't forget, this is a shortcut actually. It'll save you some time. We're going to find the noble gas that comes before the element, the closest one before it. Place the symbol for the noble gas in brackets and then use that as if it's a landmark and continue the electron configuration from that noble gas. So we're going to do Fe. Fe is in the 4th row, so find the noble gas in the previous row in the 3rd row, which is argon. And then we pick up from there. It'll be argon, and then 4s2, 3d, 1, 2, 3, 4, 5, 6, 3d, 1, 2, 3, 4, 5, 6, yes. So, argon, Ar, 4s2, 3d6, and we could do the orbital diagram too. Just do 4s, 2, and then 3d. Remember, d has five orbitals on it. 3d6, so it's going to be 1, 2, 3, 4, 5, and then 1 going down, 6. Zirconium. All right, that's in row 5. So we want to find the noble gas in row 4, which is krypton, Kr, and then we go to 5s. So we have Kr, 5s2, and then 4d, I did not count, so let's go back. 4d to zirconium, it's going to be 4d, 1, 2, 4d2. So 5s, up, down, and then 4d, 1, 2, 3, 4, 5, and only 2 electrons, so we have 1 up, and then another up in another orbital of the same energy. Bromine. And by the way, if you're comfortable with these and you're like, yeah, I remember that, you can skip ahead past this part. Just check your answers. Br. The noble gas before it is argon once again, and Br is going to be 4p5. So Ar, 4s2, 3d10, and then 4p5. So we have 4s, 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. and then we have 4p, 5, so that's 1, 2, 3, 4, 5. So you should have 2 arrows down on that one. Then we get to osmium, which once again we're going to have to go through that F block. It is the previous noble gas for osmium is xenon, Xe. (6s2) if I remember, and then 4f14, 5d, let me double check that, 5d, which, because we're in the 6th row, right? 1, 2, 3, 4, 5, 6. Yes, so this would be 5d, 1, 2, 3, 4, 5, 6. 5d6, and we could go ahead and write this out. 6s, up, down, and then 4f. Now this, we got to draw 7 orbitals. So 1, 2, 3, 4, 5, 6, 7. And we're going to draw 14 electrons. So that's 1, 2, 3, 4, 5, 6, 7, and then 8, 9, 10, 11, 12, 13, 14, and then 5d6. 5d, and I'm going to have 1, 2, 3, 4, 5 orbitals, 6 electrons. That's 1, 2, 3, 4, 5, 6. Only 1 down electron on that. Then we get to francium. This is the one, like I said, it's easy when you're doing noble gas because it's the first element in its period. So we're going to do Rn and then 7s1, and that's all. Rn, 7s1, which is just 7s with an up arrow, and that's it. All right, so let's keep going. Okay, down here, by the way, this is just a periodic table that helps a little bit if you're struggling a little bit with the D block and the F block and just all the things to remember. This is a good reference for you to look back at when you get a little bit stuck. It shows what each row actually is on the periodic table. All right, then we get to core electrons, valence electrons, and Lewis dot structures. After that, we're going to talk about ion formation and effective nuclear charge. I'm going to do one more page, I think, and then we're going to do a page break. So core electrons are electrons that are in the lower energy levels. And the valence electrons are electrons in the outer or highest actually, energy levels. The ones that are responsible for elements' behavior are valence electrons. So those are the ones we focus on mostly, because these are the only electrons involved in chemical bonding, whether it's ionic, covalent, or metallic. We have some examples here. You need to know how to find your valence electrons from any of these scenarios. You should know it's the highest principal energy level. So we're just looking at that large number in front. So in this first example, A, I notice 4 is my highest principal energy level. So the only electrons that count are the electrons in the 4th energy level. And there are 2 valence electrons because this little number 2 tells me there are only 2 electrons in the 4s sublevel, and that's all that I have in the highest energy level. In the next drawing, I see that 2 is my highest energy level, so I'm only going to focus on the electrons in the 2nd principal energy level. 1, 2, 3, 4. I have 4 valence electrons. And then finally, I have 3 as my highest energy level here. And all of those electrons I just circled are valence electrons because they're all in the 3rd energy level, so I have 7 valence electrons. There's a trick for finding those, but you do need to know how to answer questions in this method. Lewis dot structures are symbols that represent the electron and its valence electrons specifically. So let's look at this electron configuration where we have Ne3s1. Again, 3rd energy level, I only have 1 valence electron here. My chemical symbol, well, Ne3s1, let's find out what that is. Look at our periodic table. Ne is right here, and then 3s1, 1, 2, 3, s1, that's sodium, that's Na. Na is the chemical symbol, so don't fall into the trap where you just say, oh, Ne is my chemical symbol. No, you need to look and see what that electron configuration actually represents. So our Lewis dot structure, because there's only 1 valence electron, we're going to have 1 dot. So the Lewis dot structure is Na with a single dot. You could have that dot on the side or on the top or the bottom. It doesn't matter, but 1 dot. 1s2, 2s2, 2p4. All right, these are my valence electrons. 2 plus 4 gives me 6 valence electrons. The chemical symbol for this, well, 2nd row, 2p4 was the end of it, so the 2nd row, the p block, 1, 2, 3, 4, that would be sulfur. 2p4 is sulfur. My Lewis structure would be S with 6 dots. 1, 2, 3, 4. I always put 1 dot on each side before I come back and double any of them up. Okay, 1, 2, 3, 4. Then 5, 6. That'll work. And then our last example here, 2s2, 2p6, because I'm counting the arrows, 2s2, 2p6. 2nd row, p block, the 6th element is neon, Ne. So this one is Ne. It has 2, 4, 6, 8 valence electrons. So its structure is going to be Ne with 1, 2, 3, 4, 5, 6, 7, 8 dots around it. All right, magnetism. Paramagnetism is attraction to a magnet. This is caused by unpaired electrons. Diamagnetism, the lack of attraction to a magnet, is caused by having no unpaired electrons. So we've got some examples down here. When we say paired electrons, we mean that there's an up arrow and there's a down arrow. All right, so I have 2 unpaired electrons here. Let's see what this element is. I've got 3s2, 3p2, 4, 3p4. 3rd energy level, p block, 1, 2, 3, 4 is sulfur. All right, and I would call that paramagnetic. Another way of looking at it is if you've got parallel spin, you've got parallel spin in the same sublevel. That's a paramagnetic element. All right, He2s2, 2p6. Well, you got to draw the orbital diagram to really know. So we're going to say 2s, 2, and then we have 2p, 1, 2, 3, 4, 5, 6. So I don't have any unpaired electrons. Every electron is paired. 2p6 would be neon, and it is diamagnetic because all of the electrons are paired. And then we have 1s2, 2s2, 2p6, 3s2, 3p3. We got to draw those last couple. So 3s2. Then we have 3p. 1, 2, 3. By the way, if you're not following Hund's rule, you'll answer this question incorrectly. 3p3, I've got 3 electrons that are unpaired, so that makes it paramagnetic. Now let's look at what it is. 3p3, third energy level, p block 1, 2, 3, that's phosphorus. All right, and then I have 4s2, 3d10, 4s, 2, 3d, 1, 2, 3, 4, 5, and it says 3d10, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. All right, 3d10. No unpaired electrons, so this is diamagnetic. And our element here is 3d10. 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's zinc. Zn is the element. All right, which examples above have filled valence level? The filled valence level, that means it's in the noble gas section, but their energy level, the highest energy level, is full. So we're looking at our highest energy levels here. 4s2, that's not full. I have 2 plus 3, that's not full. I have 2 and 6, that's full. Okay, it looks to me like we only have one, and that is neon, which makes sense because neon is a noble gas. All right, I'm going to pause the video here. We will continue on with more and finish up these notes in the next video.